Hello, I welcome everyone listening to this presentation. My name is Ozioko, and I'm from Bendable Electronics and Sensing Technologies Group, BEST Group, from the University of Glasgow in the UK. Today I'll be presenting to you our work on 3D printed capacitive tilt sensor. The authors of this work, as shown on the screen, myself, Ozioko, and Habib Nassar, Christopher Muir, and then Ravinder Dahiya. And we all are from Bendable Electronics and Sensing Technologies Group, from the University of Glasgow in the UK. I'll go straight to the outline of this presentation. Here is the outline of the presentation. I'll first talk about the motivation, the device structure, the fabrication steps, the device characterization, results, conclusion, and acknowledgements. Let's go straight to motivation. Here is the motivation of the work. Given that multi-material 3D printing is being explored currently, and a lot of materials are emerging that are used for 3D printing, including new multi-material 3D printers. Today, we are considering using same method to print a tilt sensor, which will be part of the structure of the robot itself. So the sensor and the structure of the robot's hand will be printed as one. And then this finds also application in fluid level sensing, with sensor printed as part of the container structure. I will go to the device structure and then explain what we have done. The device structure and working principle. Here we have considered using the 3D printed interdigitated capacitive sensor as a means to sense the fluid depending on the orientation of the device. We have included 4 of these sensors: sensor 1, sensor 2, sensor 3, and sensor 4, as we can see from figure A. And then inside this is a fluid, and this fluid enables the capacitance of these individual sensors to change depending on the orientation of the sensor. So like we have in figure C, where the fluid is at a certain level and the capacitive sensor is being dipped inside the fluid, the capacitance of this sensor changes depending on the level of the fluid. So we are considering using the same concept for the tilt sensor, in which the direction of tilt of the sensor is determined by the level of fluid that flows to each of these sensors. So if you look at figure B, we have 2 heights, H, and then another one, X, and then theta. So theta is the orientation of the sensor, and eventually the orientation of the object where the sensor is integrated. So depending on the height that is covering the capacitive sensor and the height that is not covered, the orientation of this sensor can be estimated using the equations that we have below, where sine theta is equal to h0 over h. H is the height of fluid at theta equal to 0, and then h0 is the height of the fluid at theta equal to 0, and h is the level of the fluid covering the sensor. And to find out the capacitance of each of the sensors, C is equal to CA plus CL, which CA is the capacitance of the sensor in the region that is not covered, and CL is the capacitance from the region that is covered. So we go to the fabrication steps. So first of all, I will talk about the 2 different things that we fabricated in this work. First, we fabricated single 3D printed capacitive sensors, as we can see on the screen. These single sensors, we used it to check how their performance will affect the tilt sensor which we intend to fabricate. So first, we fabricated 4 of these individual 3D printed capacitive sensors, and we tested them, we characterized them to see their performance. And based on their performance, we were able to choose the size of the electrode, because we use interdigitated and know the space that is suitable for us, the gap between the electrodes. So we optimized that, and then after that, we now fabricated the tilt sensor itself, which contains 4 of these sensors printed as one structure using conducting electrode and also PLA material. So the base material that we used is a PLA polylactic acid, while the electrify is the material we use for the electrode. And during the printing, instead of attaching electrodes at the pads at the end of the printing, like we have in figure A3, instead of attaching parts here at the end of the printing, we decided that it is better during the printing to integrate the conducting electrodes for contact at the same time. So we paused the printing along the line, and then we used single strand of electrode to connect to the parts where we're supposed to take contact from, and then use silver paste to attach them. And after that, we resume the printing, and then the other layers now printed on top of the wire. So before resuming the printing, obviously we left the silver paste to dry at room temperature. And after that, we poured fluid into the compartment where we have the space for the fluid at the center, as we have in figure B2. There's a space here that we have for the fluid. So we used Ecoflex in this case, and we poured it here and used the tip, which we printed for covering it, to cover and then print on top of that lid. So I will go over now to the characterization. So the device characterization, like I mentioned earlier, in the device characterization, we first characterize the single capacitive sensors. So we characterize them individually by inserting them into EcoflexTM and removing them at certain speed using a linear stage. So we use a linear stage and then program it through computer at different frequencies. And we use the 0.625 Hertz, and we control them at different heights to measure the capacitance of this sensor at different heights, which is immersed in the fluid. So we immersed this capacitive sensor into EcoflexTM gradually at different heights, and we were able to measure their capacitance. With that, we'll be able to estimate also how much this is going to affect the 3D printed tilt sensor itself, because the tilt sensor is also based on the same principle, because it's using the principle of capacitive fluid level sensing. So if you look at figure B, that is where we characterize the tilt sensor itself. And we did this using the goniometer. And then the goniometer was able to give us the variation in angle from -20 to 20 degrees. And we were able to measure what is the capacitance of each of these sensors at that angle. So we have a sample holder here, which we use to hold the sample. And then we attach the sensor on top of this, and then connected the contacts to LCR meter, and we're able to measure the capacitance from there using a computer controlled LabVIEW program. So here is the result. First, in figure B, what we have there is the result of the individual capacitive sensors: sensor 1, sensor 2, sensor 3, and sensor 4. So like I mentioned earlier, these sensors were characterized in order for us to understand how their performance is in terms of the fluid that we are using. And from there, we can see that they are it quite gave a linear response. And what we have as insets is the loading and unloading of this capacitive sensor, and we can see a little shift from the base. It did not return perfectly to the base at the end. And what we have in figure C is the response of the sensor for cyclic loading, where we dip and remove the sensor at 0.625 Hertz, and then we're able to see that the sensor is relatively stable, as we can see in the insets on that figure C. We can see from the inset that is relatively stable. And we move to the next results. So the next result here is the result of the tilt sensor itself, where we measured using the goniometer, we measured the tilt from minus 20 degrees to 20 degrees. That is the capability of the goniometer. And we were able to record the capacitance, the change in capacitance. And from there, we can see that if we compare what I showed previously in as the results, I mean here, figure B here, if we compare this figure D with what we have there, we were able to see that approximately 6.7 degrees for every 1 millimeter change in fluid level is what this sensor is able to give us. And the length of the sensor used is approximately 12 millimeter in length, and we observed that it is possible to detect a change of plus or minus 93.8 degrees. And also from this plot, we can see 0.1% relative change in capacitance per degree for an angle range from minus 20 to plus 20 degrees. And this is what we did for us to know how this tilt sensor is going to help us. And obviously we used only one fluid, but we are hoping to use more fluid in the future to vary the type of fluid, because they will give us different results based on their dielectric. So we go move over to the conclusion. Okay, from this work we have presented to you today the 3D printed capacitive sensor, which I mentioned we had individual sensors, first of all, to characterize their performance, and then we used the same specification to print a tilt sensor for fluid level and tilt sensing application. Then the result of the 3D printed sensors were used to fabricate the fluid-based printed tilt sensor using EcoflexTM. And the result shows the ability to sense a tilt angle of approximately 93.8 degrees. The study carried out in this work finds application in robotics as well as in fluid level sensing, which the sensor and the fluid container could be 3D printed as one structure. Future work, like I've mentioned also earlier, will involve further studies with different fluids, having different viscosities and relative permittivity. This will help us to better understand what fluid is best for our sensor, because the viscosity also affects the speed of the tilt. Because depending on how you tilt it, it will also vary, depending on the viscosity of the fluid, it will also vary the response of the sensor, both response time and also the speed. Acknowledgements. I would like to acknowledge our funders and also University of Glasgow and the JWNC. These are all people who contributed in one way or the other to ensure that this work is realized. Thank you very much. This is Bendable Electronic and Sensing Technologies Group. We are in Glasgow, like I mentioned at the beginning, and you can reach us through our website or YouTube channel, through Twitter. And if you have any question, you can email, you can see the email that is there, and then we'll be happy to welcome you and welcome your questions. Thank you very much.